All right, here we are in Module 6, and we're going to begin our study of galaxies. And in this module, almost everything we're going to do at radio wavelengths. Now, before we get into it, let's just have a brief summary, an overview of the different types of radio observations we've learned how to do so far in this course. Right from the beginning, we learned how to map. Remember, single dish radio telescopes, for the most part, are essentially single pixel cameras, single pixel detectors. And so if you want to make an image, you have to move the telescope around. You do a mapping pattern, such as a raster pattern, where you zig and zag over a part of the sky. Then you take that stream of data after the fact, reassemble it into an image, correct for all sorts of contaminants, and make a picture of the invisible sky. So you can see, you can visualize the invisible. And we did that mostly over sources, though on occasion we would map a larger region of the sky. Okay, mapping, that's one mode of radio observing. The next mode we learned was timing. We did this with the pulsars. The pulsars are pulsing at a pretty rapid rate. And so what we do is we don't map that region of the sky. We just point the telescope right at the pulsar and we collect data at a very high cadence. And we study their temporal properties. Okay, so that's timing. There's all sorts of stuff that we learned from doing timing observations of pulsars. Now, in this module, we're going to learn yet another way of observing, and this is a spectroscopic observation. And radio telescopes are pretty cool, most of them anyway, in that when you take a measurement, you're getting not just an intensity at that part of the sky, but you get a full spectrum. You could do this at optical wavelengths, but it's much more complicated. At radio wavelengths, you essentially get this for free, a full spectrum. And that's interesting because in the radio, in the L band, there's a very famous, very important emission line caused by cold neutral hydrogen. And it's so important because the vast majority of the universe is cold neutral hydrogen. So let's think about what we may already know about emission lines and emission lines from hydrogen in particular. So what we're looking at here is the Bohr model of the atom, of a hydrogen atom. And so the nucleus of a hydrogen atom is just a proton, and around it you have an electron. And thanks to quantum mechanics and wave physics, that electron can't exist at any radius away from the proton, but just at certain, very well specified radii. And we call these the orbitals. You have the ground state, the first excited state, second excited state, and so forth. And if the hydrogen atom gets excited, absorbs some energy, either by absorbing a photon or it ran into something, something ran into it, transferred some energy, the electron can find itself in one of the higher energy orbitals. But then after a certain amount of time, it will decay back down to a lower orbital, and that energy difference will be released as a photon. But these are all relatively high energy photons, either in the optical regime or the infrared or the ultraviolet. In fact, in this course, we've spent a lot of time observing things in H alpha. That's this transition right here from the second excited state down to the first excited state. But all of these transitions are much higher energy than the radio. So how do you get an emission line out in the radio? This occurs completely in the ground state. And so we call this the H1 line. H1 corresponds to cold neutral hydrogen gas. It's neutral because you have both a positive and negative charge. It's cold because if it were hot, the electron would be in some higher orbital. The fact that it's in the ground state means we're talking about cold, neutral gas, but that's the most abundant thing in the universe. So this is rather important. Now, how do you get an energy transition if it never leaves the ground state? Well, both the proton and the electron are charged, and they spin. And if you have a spinning charge, you get a magnetic field. So each of these little particles act like magnets, like little bar magnets. And I don't know if you've ever played with bar magnets before, but there are two possible configurations. Either they're aligned with the north pole up on each and the south pole down on each, or they're anti-aligned, where north is up on one and down on the other, and vice versa with south. Now, if you've played with bar magnets, you know that in the aligned configuration, it takes energy to hold them together. They don't like it. They want to fly apart. So it's a higher energy state. In the anti-aligned, they want to stick together. You don't have to expend any energy to hold them there. So that's a lower energy state. Now, hydrogen can get into the higher energy state quite easily. It just has to be jostled. You bump it gently, and you can transfer enough energy to put the electron in that higher aligned state. And then you just wait. Assuming the hydrogen atom doesn't bump into anything else, after a certain amount of time, it decays. And that amount of time we characterize with something called the half-life. If you had a whole sample of these in the excited state, after one half-life, half will have decayed to the lower state. After another half-life, half of what's left would decay, and so forth and so on. Now with hydrogen, that time scale, that half-life is 11 million years, a very, very long time. Given such a long time, you may not expect to see any of this emission. But there's so much hydrogen out there, it compensates. Now, I should say, when it transitions, it releases the energy difference as a photon, a low energy photon. This is a low energy transition, and we see it in the radio at 21 centimeters, or in frequency, that's 1420.4 megahertz. Okay. So here's an optical picture of the Milky Way. The center of the galaxy is at the center of the picture. The plane of the galaxy is stretched out across the picture. You can grab the left and the right and wrap it around your head, because the galaxy is actually all around us. What's this look like at 21 centimeters? Looks like this. So this is a map of where the cold, neutral hydrogen gas is in our Milky Way galaxy. It's concentrated in the plane of our galaxy, which is where stars form. And that's how we get all this blue light and dust from the stars that formed in this gas here. Now, if you took our OPUS course, we study this in one of the labs. We take spectra at different places along the plane of the galaxy. We see the 21 centimeter H1 emission line. We measure properties of it. And through these properties and these measurements, we literally weigh the Milky Way galaxy, which is pretty cool. In this course, the multi-wavelength universe course, we're going to do something similar, but for a more challenging target. We're going to do it for Andromeda, our sister galaxy. Andromeda is in the same local group as us. We are the two gravitational centers of our local galaxy group. We're bound to each other. And from everything we can tell, we're very similar. That's why we call it our sister galaxy. It's about the same size as our galaxy. It's about the same mass. We're both spiral galaxies full of cold, neutral hydrogen gas. And so just as we see H1 21 centimeter emission from our galaxy, we should see it from this galaxy. But it's not just a matter of detecting the cold neutral hydrogen. We're going to use the cold neutral hydrogen to measure properties of this galaxy. How fast is it moving towards us? And how fast is it rotating? And for that, we're going to use the Doppler effect. So in the top figure, we have a source that's stationary. It's emitting light or radio waves, whichever, and each concentric circle here corresponds to the crest of a wave. So the spacing between them is the wavelength. Now, if the source is stationary with respect to us, we receive the same wavelengths as it emitted. We receive the light at the same frequency that was emitted. But if the object is moving towards us, and Andromeda is moving towards us, then the waves get compressed in the direction of motion. So the wavelengths get smaller, the frequencies get higher. If an object is moving away from us, some of the galaxies we'll study a little bit later on, they're all moving away from us. In that case, the waves get stretched out. They get longer in wavelength, lower in frequency. So by measuring where this emission line occurs, we can figure out the bulk motion of our galaxy. There's a second property that we can discern as well, and that is the rotation. I said Andromeda is moving towards us, but it's rotating as it does. So one side is rotating towards us, and one side is rotating away. And so the side that's rotating towards us will be even more blue shifted, and the side that's moving away will be less blue shifted. That spreads out the emission line. So from the location of the emission line, we can figure out the bulk motion. From the width of the line, we can figure out the rotational motion. And once we know that rotational motion, we can do a little bit of physics and figure out the mass of the galaxy. How much mass has to be there to make it rotate at that speed? Okay, I'll stop this video here.